We've learned all the reactions that we're going to learn in Chapter 7, and we've got one more type of, actually a new type of problem that we're going to start working on, and these have to do with synthesis. So what these will involve is stringing together a series of reactions to connect or to convert one molecule into another. These types of problems are important both because organic synthesis is an important way to make materials, drug molecules, different useful organic chemicals. It's also a good way to practice and study and remember your reactions for each of the chapters. So let's take a look at. So in this first problem, what we're going to do is we're going to start with acetylene over here. And we want to be able to convert acetylene to each of these molecules on the right. Okay, so let's start with the top one. So notice in the top one, the alkyne is still intact. Alright, so what we really have to do is be able to add a methyl group to one end and a propyl group to the other end. So this is going to take two different alkylation reactions. Alright, so what we're going to do, remember when we do these alkylation reactions, we're going to do these in two steps. The first step let me not do it like this. We can also write this, so NaNH2 is, we can also just write it like this, NH2 minus, not worrying about what the cation or the counter ion would be there. And the second thing is we have to use an alkyl halide to add the alkyl group. So let's just start off on that left side. Let's add the propyl group. We can add either end first. It's just arbitrary here which one we want to add first. And the other arbitrary thing is what halogen we're going to use. Remember, we can use chlorine, bromine, or iodine. Alright, so in this two-step reaction, we would treat it with our base. It would remove one of these protons to form an anion, to form the acetylide anion. And that anion would do a substitution reaction replacing the bromide. Okay, so we're going to end up with this 3-carbon piece attached to the alkyne, and we still have an H on the other side. Alright, so we're halfway there. So for the next one, we want to add a methyl group. Alright, so it's going to be the same thing, NH2 minus. The second one, we need to add a methyl group with a halogen. Let's say we use iodide this time. So again, in this case, what we'd be doing is removing the remaining proton on the alkyne to form a new acetylide anion, and that would do a substitution reaction with the iodomethane to give us our product. Alright, so this one is just two steps. And in each of the synthesis problems that we're going to be doing in the near future, these types of steps are going to be involved. We're going to start with acetylene. We're going to stretch out or lengthen the carbon chain, and then we're going to manipulate the functional groups. Alright, so let's just write these. They're going to be two parts. Okay, first part, extend carbon chain. Okay, and this is going to involve these alkylation reactions. And then the second part is going to be manipulating the functional group. So we can just call these functional group transformations. Okay? Remember that so far we can only do these alkylation reactions with an alkyne. Okay, we can't do it with an alkene. So if we look at our next two compounds, notice that in each of these cases we have an alkene, and since we can't extend the chain with an alkene, we know that we have to make that alkene from an alkyne. Right? So let's work backwards here. Okay, so for each one of these. All right, to make a trans, well, let's just draw the alkyne then. All right, so we're going to have an alkyne. Looks like this. Triple bond and a methyl group. So that, in fact, is the one that we already synthesized, right, up above. And we're going to use the same one here. All right, so how do we convert the alkyne to a trans alkene? Trans. All right, well, we're down here, we've got to have a cis alkene. All right, so we got to know our different reagents. Remember, if we want to add hydrogen to that alkyne and get trans, then we'd use what we call the dissolving metal reduction. Okay. So we use sodium and liquid ammonia at a cold temperature, and that gives us the trans alkene. All right, if we want to get the cis alkene, what do? All right, in this case, we use hydrogen, and remember we use this modified catalyst called the Lindlar catalyst. Okay, and that gives us the syn, or the cis alkene. All right, so both of these then would take three reactions, right? So we would do these two here. We do one step here, second step. This molecule is the same as these, and then we do one more step to make the alkene. All right, so when we do our synthesis, we're going to follow this strategy. We're going to extend the chain, then we're going to modify the functional groups. Once we get to the extended chain, like up here, we could do any of our reactions that we've learned for alkynes, right? We could add halogens, we could add HBr, we could hydrate it, we could hydrogenate it all the way to the alkane. We can do any of that chemistry. Once we convert it to an alkene, though, so one of these compounds here, then we have all of the reactions that we learned for alkenes available, right? So we could do hydration reactions, we could do brominations, we could do all that chemistry that we learned before. All right, so that's the way that this is going to. Let's look at some that are slightly more complicated. So again, in each of these cases, we're just starting with acetylene. And we have various functional groups in our product. So one of the important things in our analysis here is that we know that the functional groups in our products have to be located in a position that would be part of the alkyne originally. All right, so for example, this first one, we have this dibromide. These two carbons here are going to be the ones that have to come from the alkyne. All right? So let's move backwards one step. Okay, so we have these two bromines, one's coming forward, one's on the back side. So how would we make that? We'd make it straight from the alkyne? No, we can't make this from an alkyne, but we can make it from an alkene. From this alkene, we can just use Br2. And remember, when we add bromine to the alkene, this is an anti-addition. And so it gives us the two bromines on opposite sides. All right, so how would we make this alkene? All right, we've got a trans alkene, so like on the previous slide, we could make that with a dissolving metal reduction. gets us back to an alkyne. Alright, and then it's going to be similar to the last slide as well. So I'm going to have to try to fit all this in. We're going to add one group to one end of the alkyne to acetylene, the other group to the other end. So let's do first, we can add NH2-, the base, to remove the proton on acetylene. And then we can add an alkyl halide. Okay, so we're going to add well, this would be 1, 2, it would be 2-methyl, 1 bromopropane. Okay, so we do that, and we have this alkyne, and then we have to add a methyl group to the other side. 1, we use NH2-, 2, we could use methyl bromide again, or something like that. Alright, so again, 2 steps, 2 parts. We extend the carbon chain, and then we manipulate the functional groups. Alright, let's look at the next one. Alright, so in the next one, we know that this carbon right here has to be part of the alkyne. Right? So we could either have an alkyne that was on this position, or we could have an alkyne that's on this position. Alright? So is this going to make a difference? Right? Which of those two? Not really, because this molecule is symmetrical in that, and that ketone is right in the middle. Alright? So we can make the alkyne to either side. Now, do we make the ketone directly from the alkyne, or do we need to make it from an alkene again? Well, we make that one directly from the alkyne. Alright, so let's see, what do we have? 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4. Let's do it like this. 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to put it there. I guess I put it on this side where it was in red. Okay, so either way, we get 1, 2, 3 heptine. Okay, so how do we do this conversion? Alright, so this is basically just a hydration reaction. Right, but remember in this, what happens is we add water, OH goes to one side, H to the other side, and then this enol tautomerizes, okay, to give us the ketone. Alright, so would there be any other products that we might get in this step? Well, yes, because the OH could add to the other side of the alkyne as well. Alright, so we could also get this enol. And what's that enol going to give us when it tautomerizes? Okay, that one is going to give us this. This ketone, are those two the same? No, these are different. So we'd end up just getting a mixture here. So if we wanted the one that I started with, we just have to be able to separate and purify that mixture. Okay? So how do we get to here then? Right? So to get to here, we're going to go through the two-step process again. We're going to use NH2-. Let's say we put on the propyl group first. We could do the ethyl group first if we wanted. Okay, we get to here. We do this a second time. Now we're going to add an ethyl group. Okay, and then we've done our our chain extension, or we've got our carbon framework, and then we manipulate the functional group. We convert that alkyne into the ketone. All right, so what about the last one? Okay, so the last one, right, so the alkyne has to be attached to this position right here. All right, so we could have the alkyne being here, or the alkyne could be here. All right, so let's just draw those in. Okay, so this could be here, or it could be like this. Let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, like that. Okay, so how would we do that? Okay, so what we would do is we'd add HBr, and we'd have to use an excess, or at least 2 times of this. All right, now, is there a difference, or is one of these alkynes better than the other for forming this product over here? All right, so in fact, the top one there is going to be better, right? Because now we have a terminal end and we have an internal end, so there's a terminal one. So when we add HBr, it's going to follow Markovnikov's rule, and both bromines are going to go right here, just like we want. If we started with this other compound, because both ends have carbons on them, the bromine could go to this side, or it could go to this side, the first one, and then the second one would go there too, and so we would end up with this compound and another one with 2 bromines over here. So we get a mixture, whereas we get a single compound over here. So in fact, this one here in this case is going to be the better choice. Alright, so then we can make that just in one step, because we only have to add an alkyl group to one side. Let's use chloride this time, like that. Alright, not too bad. Alright, so look at these different functional groups that we want to form. Okay, so again, we know that the functional group, here we've got this alcohol, has to be attached to the alkyne. So this alkyne is eventually going to have to be right here. All right, so we see that we're only going to have to add an alkyl group onto one side. Can we make this alcohol directly from the alkyne? No. Remember, if we try to add an alcohol, if we try to do a hydration to an alkyne, it forms a ketone or an aldehyde if we use the hydroboration one. So what we really need to do is we need to make this from the alkene. All right? And so how would we then put an OH on the end? All right, so we want to do a hydration reaction, but we want to do a anti-Markovnikov hydration reaction. So this is going to have to take the hydroboration oxidation reaction. Okay, so we use hydrogen oxidation step, hydrogen peroxide, hydroxide, and water. Okay, so that's the anti-Markovnikov, because the OH is going to the less substituted side. Alright, so now, how do we make this alkene? Alright, so we're going to make that alkene from the alkyne, from here. So, because there's just 2 H's on the terminal end, we could make this either of 2 ways. We just need a method that stops at the alkene. So we could either use H2 and Lindlar's catalyst, or we could use the dissolving metal reduction. Either one would be fine. Okay? And then, of course, to go from here, we've been doing this kind of chemistry a few times now, NH2 minus, followed by, let's use bromoethane this time. Okay, getting the hang of this, hopefully. Alright, so let's look at this next one. Of course, the alkyne will have to be here, right? So, look at that. We're going to put two groups on at the same time, right? There's no pi bond left, so we're going to have to make this one from the alkene. Right? And how can we put a bromine and this methoxy group on at the same time? Okay, remember that we can use bromine, and if we use bromine in methanol, then the bromine reacts with the alkene to form the bromonium ion, and then the methanol acts as a nucleophile, and it comes in at the more substituted end. So that would give us that product. Okay, so of course we need to get the alkene from the alkyne. And of course we can use the same methods as up there. Okay, either one, because it's a terminal one. And then we just have to add a single alkyl group. NH2 minus, Br, something like that. Okay, so we extend one end. That gives us the carbon chain that we want. Right, we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We have the whole carbon chain. And then we have to start manipulating the functional groups. So then we're going to hydrogenate this or reduce it and then do this bromination reaction. Alright, what about this last one? What kind of functional group is that again? Right, remember this is called an aldehyde. How are we going to make an aldehyde? Okay, the aldehyde is going to come from an enol like this. And how do we make an enol? We make an enol from the alkyne right? But we want the enol on the end, so this is an anti-Markovnikov, so we have to use a hydroboration. So we use this borane that has two R groups on there. Okay, and then the second step is the same. We have hydrogen peroxide, hydroxide, and water. Okay, so that does our anti-Markovnikov hydration, gives us this enol, which then tautomerizes to the aldehyde. Alright, and then, of course, we've made this one before. We just do this with NH2 minus. This is just like that top one up there, right? Alright, what did we use last time? We used bromine. Okay, extend the chain, manipulate the functional groups. Alright, so we have made it through. From the beginning, we just learned about naming, we talked about structure of alkynes, we learned about reactivity, and we added these 4 types of groups. We talked about the acid-base properties of terminal alkynes and the fact that we could deprotonate them to form acetylide anions, which can do substitution reactions to form carbon-carbon bonds. And then in this last video, we've looked at ways we can combine strings of reactions to convert acetylene into various different molecules. All right?